Next circuit, we're going to talk about an automatic gain. So what's going on is we have a V out here, and it goes into some sort of peak detector, and this drives the signal to say, turn down the gain on this guy. If the signal is too big. So we have the equations for the transconductance, how the Vn relates to let's see, there we go. This is the V out. This is V out right here. These two expressions are V out. Now, IABC can be programmed through the second one. So this is a constant voltage of some sort, and this is V out. So we get an equation like this. We solve it for V out, and we get this, that when V in is too big, it starts cranking the gain down. These are your red bars. When you look at your microphone and you're talking and you see the red bars on the little meter there, that's what's going on. Your signal is probably not going to be a good quality. It's not going to faithfully represent your input when this happens. This tries to adapt to it as best it can, but it's not perfect. Okay, we can simulate, we can also simulate inductors, by the way. So here we have an integrator, which is like a capacitor and a resistor. And we've seen this already on an earlier slide. Okay. Yeah, we got to solve for V out. This guy right here. And is this a, yeah, this is a simulated resistor, 1 over GM2. There it is. There's the 1 over GM2 right here. And this is the initial gain, the first stage gain. Okay. It is a pole, so it's going to start flat and then it's going to decrease. So this is a low pass filter. Frequency given by this here, you'll notice. Okay. So here we're doing a specific design. You guys go ahead and figure this one out here. We're trying to design for a specific gain. So we need the original gain to be this. And we can look at the previous slide. There we go. GM1 over GM2 has got to be 4. And going back again, J omega C over GM2, C over GM2 has to equal this. This factor right here. Did I get that right? Yeah, there it is. So now we just figure things out. There we go. This is expressing the first thing I said. So I can erase that. I'll go a little further. And that expresses the second thing I said. This is omega C. And so GM2 over C. You'll notice they flipped it compared to mine. Okay, I'm going to get rid of my ink so you guys can see this a little better. There we go. So this is what I just talked about. Both these equations. 3 unknowns. So we need to program GM1. This is a design problem. We need to do some reasonable values here. And so we have 2 equations. We're trying to figure out these 2 things. And we have the variables are the capacitor and the 2 GMs. So you pick one, like the capacitor, and then figure out the other 2 from there. And check that it's okay. Remember, GM has to be in a certain range. 15 times 10 to the minus 6 is bigger than this. Yay. And it's smaller than this. Then we can figure out what the current has to be. And similarly, we can do the same thing. Let's see, 62 micro Siemens, which is 62 times 10 to the negative 6. Yay, we're okay. It's below 1 millisiemen. A millisiemen is 1,000 microsiemens. So we're okay. We're rocking and rolling here. Not going to go through the details of this. But you can program, the trick is with this, depending on what A, B, and C are, you can program it to be a low pass, band pass, or high pass. Now, as we're going to see in just a minute, A is, for this circuit, A is going to be 0. And I'm just going to zip through it. I'm not going to go through the math, which is hairy, as you can tell. We don't have an omega squared term on the top. We have the constant term C and a constant term B here. But we don't have an A. So A is always going to be 0. So we can't do the high pass. But we're going to have 1 0 and 2 poles due to the squared term down here and the omega term up top. So depending, you can do various things with it. The band pass, for example. What you're going to have is, remember the pole, it's going to be flat and then it's going to drop at the various frequencies. So the high frequencies, the band pass, you're going to drop steep, 40 decibels per decade. And then over here on the other side, you're going to have a 0, which it rises as frequency increases. It starts at a constant and then gets bigger. So it's never going to be absolutely 0 unless C equals 0. Okay. Yeah, and this expresses it, by the way. If this factor here is something finite, this stuff here is something finite, and this is 0, then you have scratch this constant term out. Okay, let's move on. So all sorts of equations that go with this. Too many. So this is a design problem using the previous circuit. So they want a band pass, frequency 500 kilohertz. You got to go back to the equations on the previous slide and figure this out. So you got all these factors, and center frequency, there we go. This is omega over Q naught. That's going to be your bandwidth, by the way. Bandwidth, 75 kilohertz, so that's the second one. And we've got a nice equation for it. And then the quality, we're going to find out gain of -5, and that would be VO2 over V in. So the band pass, so going back, there we go. That would be where C is 0, the constant term is 0. There we go. We can choose either this or this to be 0 also, and to get the equations. And it depends how the equations work out. So center frequency gain of -5, and they're choosing V1 equals 0. So when at the center frequency, when the, there we go, 50 picofarad capacitors, both. So we know C1 and C2 also. So now it's a matter of number crunching. We're given the capacitor size, we can find out the gain of GM3. And we're finding out where this is the real part of the denominator. So J squared is going to make it real. And then here's the 1. You're adding the 1 over here. That's the real part. But now, remember, this is 0. You have a J on top. So it's actually the imaginary part of the gain, which you want to be close to 0. So you set this equation equals 0. Okay. And then you get the overall gain, which would be V, the second input, V out 2, which is this guy, divided by V in 2, gives you the overall gain at the center frequency. And figuring all this stuff out, you know, lots of number crunching, you get this equation here. What GM2 has to be. Now you can calculate everything else. GM1, GM3 it's going to matter. Or does it? Yeah, GM3 is here. Did we get GM? Oh, there's GM3 right there. Let's see. This is the bandwidth. Yeah. So, does this imply GM3 has to equal 23.5, 2 pi times 670 times 75, which is approximately 450 times 10 to the third. That's your bandwidth. Oh, and here we go. And when you multiply it by the 2 pi. So we got an implication. GM3 equals the bandwidth times the capacitor, the bandwidth times the capacitor. So GM3 equals, where's the bandwidth? 75 kilohertz, 2 pi times 75 E3. 75 times 10 to the third hertz. And 50 times 50 E negative 12. Okay, 7,500 pi. So that's 2 pi times 75 times 50. 50 times 2 is 100. So 7,500 pi. And then now we have to take care of the exponents. E negative 9, 7.5 E negative 6 is GM3. So, and then figure out the current for that. Okay. Yeah, this does make sense now. Where's my, yeah, this makes sense. You have to solve for GM3. This is a, they leave it, the units, they leave the units weird. Because this is a farad down here. So this should be microsiemens per farad. Okay. We're going to stop here, move on to the next video. Oh, I'll stop here actually. So we've talked about this. Now this is the plot of what it looks like. So you get a nice peaked bandwidth. And you can program it by programming the voltages. You can turn the dial. That's the idea. And stopping here, I'm going to talk about this circuit next.